Following on from some of the earlier videos, we were trying to understand why it is that when you differentiate a unit tangent, it will give you a new vector, and this new vector is always orthogonal to the unit tangent. So in effect, we are trying to understand this. So think of this as being like one vector, and when you dot it with the derivative of that vector, it's always orthogonal. I know it's kind of confusing because when you talk about the position vector, you are talking about this vector here as the plane is moving through 3D space. But when you think, when you're trying to understand why the derivative of the unit tangent, you got to think, well, the unit tangent, as the plane is moving about, as the plane is moving about, the unit tangent, so this is a circle, the unit tangent is always of length 1. So this unit tangent here is this vector here. What I'm trying to say is that I know it's kind of confusing in that this is really the position vector, but you need to change the way you think. This thing here is just like a vector, any vector, and when you dot it with the derivative of that any vector, then it will be orthogonal. So rather than thinking this as being the position vector, think of this thing here as being a vector, any vector. In our case, is a unit tangent vector. This thing here. So it's moving along like this. It's moving along like this. So this thing here is a unit tangent, and then when you dot it with its derivative, it will always be orthogonal. So you can think of this as being it's the tangent of a tangent. This thing here is a tangent of a tangent, if that makes sense. So when you read this, it's really in our case, don't think of this as being the position vector. Don't think of it as being a position vector. Think of this as being the unit tangent, the unit tangent, and then dot it with its derivative. Okay, so let's start now. So in some of the early videos, we've established that we've established this step. We've done this and we've done this. It is possible to differentiate the dot product, whatever that may mean. Okay, so now that as it turns out, when you take the derivative of the dot product, it will then give you this. As it turns out, it will be the derivative of the first, and then dot it with the normal, and then the second part would be, well, you differentiate. It's similar to the product rule. You differentiate this, leave this alone. So that's similar to this, and then you leave this alone, and then you differentiate this. That will then be this. So it's similar to the product rule. So anyway, you differentiate this. That will then give you this. Now here you've got one block plus another block. As it turns out, these two blocks are the same, so you can merge them together. The reason why they're the same is here you've got the derivative and the normal, the original vector. You've got the derivative and the original vector. The reason why these two are the same is because of this. It's because they're commutative. So if you look at this, if you're trying to, let's say this is one vector u and another vector v. If you take the dot product, it would be this times this, that will then give you this. This times this, that will then give you this. This times this, that will then give you this. But then if you switch them around, so now you've got vu, it will give you the same thing. U times this, that will then give you this. This times this, that will then give you this. This time, look, these two are exactly the same. It's really this times this, but here you switch them around. So in effect, going back to here, in effect they're the same. So here you've got one block and another block. These two blocks are the same, so you can merge them together, and so you've got two blocks. And then from here, divide both sides by 2. That will then give you this. And then let me think. And then if you want to, you can switch these two around because you know they're commutative. So that really takes us to here, and this thing here is another way of writing this. So what that means is if you have a vector of equal length, remember the original statement says it must be of equal length, of constant length. If you have a vector of constant length, take the dot product of its derivative and it will always be orthogonal to that. So what that means is this: if you have a So when you read this, it's like one block dotted with another. So we are looking at the tangent. So the tangents here of equal length are not an ellipse. An ellipse is not of an equal length at any given time. So so you can see that this length is not the same as this. Well, the point is that the tangents here, the unit tangent, take the dot product, and then take the dot product with its derivative. So you can think of its derivative as the tangent here, and it's always orthogonal. Okay,